Natural experiments. This module is about natural experiments. Natural experiments are exogenously occurring events that allow comparison between treatment and counterfactual outcomes. The defining feature of natural experiments is that exposure to the treatment is exogenous and it is impossible to manipulate. When there is exogenous treatment assignment, we can draw valid inferences about the treatment effects with the help of auxiliary theoretical assumptions and careful choice of econometric methods. Natural experiments are not an evaluation method per se, but rather a source of identification of causal inference that researchers can exploit using standard impact evaluation methods. To analyze natural experiments, you can use difference in difference, instrumental variables, matching, regression discontinuity, or a combination of some of these methods. Natural experiments are used in a variety of fields, including health science, political sciences, and economics. This is not to say that all natural experiments have been analysed. There is substantial room for more natural experiments to be studied, especially in the development context where economic agents are exceptionally vulnerable to naturally occurring events. Some examples of natural variations with potential to be analysed as natural experiments are twin birth, birth date, gender, and weather events. However, natural experiments do not need to be natural. The true requirement is a transparent exogenous source of variation in the probability of receiving treatment. A natural experiment may very well be induced by a policy change, a divergence in law between regions, or even a random assignment process. Man-made events can also be considered natural experiments and can be exploited to identify causal effects. For instance, unobserved ability can bias the estimation of the effect of schooling on future revenues. Smarter people tend to study more, and smarter people also tend to earn more money. When you observe an individual with many years of schooling and a high revenue, it is impossible to disentangle if the latter is the result of schooling or if that person has simply found smart ways to make money and education does not play a role. Unobserved preferences can also bias the estimation of causal inference. The effect of fertility on women's labour market participation cannot be estimated using simple observational data. Women who like large families with many kids may also prefer working for their families at home rather than having a paid job. When you observe a woman with many children who does not have a paid job, you cannot disentangle whether this is because fertility hinders labour market participation or whether this is the result of her own personal preferences. The challenge of the researcher consists of combining information from some exogenous event or natural experiment within some valid assumptions and coherent econometric methods to identify the causal effects of such treatments. In the scientific literature, the use of natural experiments is particularly appreciated when a randomized control trial is difficult to implement or would be unethical. For instance, it would be unethical, if not unfeasible, to randomly allocate children to women to measure the effect of fertility on labour market participation. It would also be unfeasible to randomly allocate the years of schooling to different individuals to estimate the causal impact of education on earnings. In the suggested readings, you can learn more about how to use twin siblings as a natural experiment to estimate the causal effect of schooling on earnings. You can also read how to use the gender composition of siblings as a natural experiment to estimate the impact of fertility on women's earnings in the labour market. The main drawback of natural experiments derives from its very nature. the lack of control of the exogenous event that allows causal identification may also limit the interpretation of the treatment estimates. Moreover, there is a limited number of random events provided by nature that affect outcomes of interest. Using these events as natural experiments often requires auxiliary assumptions to derive valid causal inference. In this module, we will see that natural experiments share some features with random selection methods. We will draw a parallel between randomized control trials and natural experiments to highlight their similarities and key differences. These differences give rise to inferential and conceptual threats to validity that are often overlooked. I will highlight the importance of natural experiments with a famous example dating from the 19th century. A disastrous cholera epidemic illustrates why natural experiments are preferable to randomized control trials due to ethical consideration. This module focuses on natural experiments as a source of identification rather than on the specific methods required for their analysis. The previous modules equipped you with a good knowledge of internal validity and the theoretical requirements behind most common econometric methods. At this point, you should be able to select the best evaluation method to analyze a natural experiment. The question of how to select a comparison group in natural experiments is challenging. The assignment of units to the treatment is outside the control of the researcher. The main task of the evaluator consists of selecting which comparison group is more suitable to derive causal inference. Unexpected events do provide an exogenous source of variation, but they often require additional assumptions to identify the causal effects. A judicious analysis of a natural experiment should explicitly justify the choice of the comparison group as well as the theoretical assumptions required by the econometric method used in the analysis. I will present two examples from the classical literature from two exogenous events that have been exploited as natural experiments. In both cases, we will discuss their validity with respect to the choice of the comparison group. First, we will discuss a gender-based reservation system used in India to encourage women's participation in local government. Then, I will present the Mariel boat lift, a mass emigration of Cubans in 1980. At the end of this module, you should be able to evaluate the research potential of a natural experiment and recognize the assumptions required for drawing valid causal inference. Natural experiments differ from randomized control trials in at least two fundamental ways. First, in natural experiments, the assignment procedure may be exogenous, but not necessarily random, as it is in RCTs. Second, and less obvious, the group of treated and untreated individuals may not be directly comparable in natural experiments. Researchers need to carefully select which subgroups to compare. In the simplest randomized controlled experiment, units are randomly divided into two groups. One group is exposed to a treatment and the other is untreated, the control group. The random selection method allows us to compare the mean outcome of those assigned to the treatment to the mean outcome of those assigned to the control group. Units are selected into the treatment or control group based on a random assignment mechanism, for example a lottery, designed by the researchers. This random assignment prevents units from self-selecting or being selected by others into particular groups, and thus ensures that the treatment and control groups are similar in terms of all observed and unobserved characteristics. Because the only systematic difference between the two groups is the treatment that was randomly assigned, comparing the mean outcomes of the two groups provides an estimate of the causal effect of the treatment. In natural experiments, the mechanism that assigns units to treatment and control groups is not necessarily random. Rather, an event occurs in the world that happens to affect some subjects, but not others, and the researcher assumes that the naturally occurring intervention was assigned as if random. I usually refer to this as the as if randomness assumption, or the exogeneity assumption. In most studies, researchers go to great lengths to argue that the exogeneity assumption is satisfied. Exogeneity implies that the treatment and comparison groups used in the analysis of a natural experiment are similar in terms of all observed and unobserved factors that may affect the outcome of interest. If the two groups are similar in this way, then the design is said to be valid, and comparing outcomes across the groups identifies the causal effect of the treatment. The issue of comparability of treated and untreated units is a subtle question. Natural experiments generate a group of units who receive treatment and another group who do not. It is often possible, however, to define different treatment and control subgroups from one single natural experiment, yet only some of these groups are similar and thus valid to compare, even when nature intervenes randomly. Under the random selection method, the researcher picks what evaluation sample should be ex ante and then randomly assigns units to the treatment and the control groups. In a natural experiment, we find an intervention that has been implemented and also find some treated and untreated units. We then construct a comparison group to test a particular hypothesis. The comparison group selected post hoc must be comparable to the treatment group. Even if the natural intervention is truly exogenous, even if there is random assignment, comparability needs to be discussed. Understanding the process that produces the variation in exposure, the assignment process, is critical to the valid analysis of a natural experiment. We will come back to this point later with examples. All non-experimental evaluations face potential endogenous selection into the treatment. By now, you are aware of most common econometric tools and evaluation elements that can help you address the problem of selection bias. Rich data is always an asset. Accurate measurement of potential confounders can help identify the sources of bias on observables. Matching methods can be used to reduce the selection bias when the factors that determine selection can be measured accurately and comprehensively. However, there is no single approach that provides the perfect solution to unobserved selection into the treatment. First, accurately controlling for all the characteristics associated with exposure to an intervention is difficult. Second, even when controlling for all observed factors associated with exposure, the analysis is still vulnerable to selection on unobservables. Methods such as difference in differences, instrumental variables, and regression discontinuity design can deal with unobserved selection bias. Keep in mind that these methods lead to valid impact estimators under certain theoretical assumptions that are often untestable. Combining methods that address different sources of bias and comparing their results is a good way to strengthen causal inferences drawn from natural experiments. Let me illustrate the essence of natural experiments with a well-known example, the London cholera outbreak. In medical research, there is a long tradition of exploiting external shocks such as epidemics, famines, or economic crises to analyze the causes of diseases. In the history of public health, few events are as important as the natural experiment studied by the physician John Snow back in 1854 in London, England. Snow demonstrated the causal link between contaminated water and the spread of cholera. This natural experiment had strong policy implications. In the short term, this impact evaluation led local authorities to disable a contaminated well pump by removing its handle. In the longer term, subsequent investment in sewage systems helped banish cholera from London, Europe, and much of the developed world. Before this natural experiment, the most common hypothesis was that cholera was caused by miasma, unpleasant and unhealthy vapors arising from decayed organic matter. Public authorities promoted the eradication of cholera through the preventative approach of opening windows to let the miasma out of the houses. The leaflets and posters of the time make fascinating reading. The cholera epidemics provided opportunities for the public authorities to press pious temperance messages. Beware of drunkenness, nothing is so likely to bring on disease. Abstain above all from ardent spirits. Public health advice warned against long sittings, dancings, revellings, surfeitings, and mixed crowded companies in booths and showrooms. All these were proactive public health policies to avoid cholera. John Snow was sceptical of the miasma theory. He believed that cholera infection was waterborne rather than airborne. Today, we know that cholera can indeed spread via water infected with a bacterium. However, in John Snow's time, this was a controversial hypothesis. His theory, published in 1849, arguably received the very first "You know nothing, John Snow" from the medical establishment. In an effort to gather evidence for his theory of change, Snow carefully studied several cholera epidemics using maps and histograms. The interest for us is his use of the London cholera outbreak as a natural experiment to prove the causal relationship between contaminated water and the disease. By chance, most of the water supplied to London households was provided by two private water companies. The Southwark Vauxhall Company, in green, supplied contaminated water, creating a treatment group. The Lambeth Company, in red, supplied uncontaminated water and created a comparison group. At the time, the City of London would dump their sewage directly into the Thames, the city's main river. During the summer of 1858, the hot weather caused the smell of untreated human waste and industrial effluent on the banks of the Thames to become unbearable. This event was known as the Great Stink. The Southwark Vauxhall Company drew their contaminated water from the Thames River downstream from the sewage flow. The Lambeth Company had its intake of relatively clean water upstream of London. One company provided water potentially contaminated by London sewage, while the other did not. In the areas where their service delivery overlapped, the water lines of the two companies were completely intertwined. Snow argued that there was more or less a happenstance assignment of households to one of the two companies. This assumption corresponds to the exogeneity assumption, or as if random condition required for valid natural experiments. In 1854, a severe cholera epidemic struck the Soho district of London. John Snow used the exogenous institutional circumstances to test his theory. He wrote, "No fewer than 300,000 people of both sexes, of every age and occupation, and of every rank and station, from gentlefolks down to the very poor, were divided into two groups without their choice, and, in most cases, without their knowledge. One group being supplied with water containing the sewage of London, and amongst it whatever might have come from cholera patients. The other group having water quite free from such impurity." This quote means that water supply was, for all intents and purposes, independent of household characteristics. The overlap area contained a diverse population and was considerable in size. Simply examining exposure to impure water would have been far less convincing. Drinking contaminated water would likely have been correlated with poverty and other forms of environmental contamination, such as air contamination or miasma. Furthermore, the tendency to drink impure water itself is a choice. Drinking dirty water would likely be correlated with other impious behavioral choices such as drunkenness or revelling, which were also thought to influence the outcome of interest, cholera. Variation in the type of water company generated exogenous variation in exposure to impure drinking water. Treatment assignment was as good as random. The natural experiment of the cholera outbreak exploited institutional circumstances beyond the researcher's control. This is a classic natural experiment in which there is no real possibility for using random selection methods. Randomizing water sources in London would have been prohibitively expensive, but, more importantly, it poses intrinsic ethical constraints. It is unethical to use random selection methods to variate exposure to potentially harmful treatments. When an impact evaluation deliberately assigns subjects to treatment and comparison groups, the researcher has the responsibility to minimize any potential risks and to ensure that those who participate in the evaluation are doing so through informed consent. For better or worse, in natural experiments, the treatment takes place without individual consent. Researchers must still avoid doing harm in the collection and treatment of exposure data, but if they make use of existing data or secondary data, there are fewer ethical concerns. There is a wide acceptance of natural experiments as sources of causal identification for health determinants that are not amenable to randomization. For instance, unlike cash transfers, the right to food when available cannot be randomly allocated and delivered. Another fundamental principle of impact evaluation is that agents should not be excluded from an intervention that is known to be beneficial solely for the purpose of conducting research. Keep in mind that researchers are expected to follow generally accepted scientific norms and ethical principles regardless of the evaluation method. In natural experiments, ethical concerns are usually beyond the control of the evaluators. There is an infamous natural experiment known as the Dutch hunger winter. From October to April 1944, the Nazis locked food shipments to Western Holland, causing the death of more than 20,000 people. A natural experiment was created for pregnant women in that region. The excellent Dutch records make it possible to determine at what stage the fetuses were exposed to famine conditions. The analysis of this natural experiment highlighted causal links between prenatal nutritional deficiencies and several aspects of child-adult health. This analysis has resulted in useful knowledge. For instance, its findings have been drawn on to partially explain the prevalence of type 2 diabetes in India. It should be clear that researchers should not withhold an intervention from potential beneficiaries, nor put participants at risk. Furthermore, they have the responsibility to make known the consequences of harmful treatments or damaging deprivation. Rigorous impact evaluations can guide the establishment of better rules. For instance, the cholera outbreak experiment did not persuade everyone instantly, but eventually all water companies were forced to improve their services. Today, London sewage is treated to the point where water is nearly safe to drink and is returned to the Thames well downstream of London. The ethics of any impact evaluation should centre on protecting the subjects who participate in the evaluation. I will now discuss another natural experiment that exploits the Indian reservation system. These are a set of policies that aim to promote gender parity in local governments. India has a long history of using reservation quotas as a means to enhance the representation of underprivileged groups. Among other quotas, in each local government, or panchayat, election, 33% of seats are randomly selected to be reserved for women. This reservation of electoral seats for women has been used as a natural experiment to estimate the causal effects of quotas on the probability that women will contest and win elections after the quotas are removed. Few dispute that gender-based electoral quotas increase women's representation while they are in place. The open question is, what happens after the reservation quotas are removed? A convenient feature of the Indian system is that reserved seats are chosen through a random lottery system. A seat might be reserved for women in one election and then open to anybody in the following election. This random allocation rule creates a natural experiment. Notice that natural experiments are not necessarily associated with natural events, biological or meteorological incidents exempt of human intervention. Natural experiments refer to assignment mechanisms that arguably mimic random assignment to treatment, but cannot be modified. Unlike other natural experiments, the mandatory Indian quota fully respects the as-if-random assignment to treatment assumption. The seat reservation process is known to be random. In each election, each seat is randomly assigned either to be reserved for a female candidate or not. In 2009, Rikhil Bhavnani intended to use this random selection process to investigate whether electoral quotas for women alter women's chances of contesting and winning a seat in the local government after these quotas are withdrawn. In 1997, around 1/3 of the wards or seats in the local government were randomly selected to be reserved for women representatives. In the following elections in 2002, a completely new group of wards was randomly selected and reserved for women. Because of randomization, whether a ward is reserved in 1997 is independent of whether it is reserved in the next elections in 2002. It is possible to define and compare a variety of different treatment and comparison groups in this natural experiment. The author focuses only on wards that were open in 2002 and discards reserved seats in that year. The original intention behind keeping wards that are open in 2002 is to mimic a world in which no wards are reserved and there are no reservation quotas. The essential assumption behind this comparison is the absence of interaction between the two treatment assignments. Notice that this assumption is by no means linked to the randomness of the treatment assignment in the two periods. This design assumes that open wards in 2002 would have had the same outcomes if there had been no reservations at all that year. Let's discuss the general effects of quotas and why this assumption might be invalid. The main argument is that reservation quotas could have an effect on the unreserved seats. Suppose that you have an underrepresented group that you want to encourage to participate in the government. You select some seats to be reserved for that group. Reservation should increase the number of representatives of the minority group, but could also implicate a social cost. Some of the reserved seats could be occupied by less able candidates than otherwise. In many cases, when reservation policies are implemented, the social benefits of diversity are thought to be higher than the potential cost of a suboptimal selection of candidates. Although quotas have been shown to have an overall positive effect on minority representation, the social cost of reserving seats could be amplified by a negative effect. A reservation system could have potentially adverse effects on open wards. If minorities are not allowed to run for unreserved seats, and those open seats are assumed to be reserved for the dominant group, in that case, the reservation policy would simply displace good minority candidates from their open seats to reserved seats. In this situation, the social cost increases. As before, some of the reserved wards could be occupied by less able candidates than otherwise. In addition, the open wards previously occupied by the minority may also be occupied by less able candidates after reallocation. These kinds of negative effects could arise if reserved seats occupied by women are viewed as depriving men of their chances. The reservation policy could spill over the unreserved seats, reducing the number of women candidates in open wards. The reservation policy in 2002 may have influenced the number of female candidates who run for open seats in that year. If political parties are able to discourage more women from running in 2002 open wards, when those wards were also open in 1997, then there is an interaction between the treatment effect of 1997 and the treatment effect in 2002, even if there was random assignment. In other words, if a ward is assigned to be open in both 1997 and 2002, the grey units in the image, women may be less inclined to contest those seats than men. This situation creates a biased counterfactual in 2002, because the grey zone does not contain the number of female candidates that would have run in the absence of the reservation system. The difference between C and D would result in a biased estimate of the treatment effect. The reservation system would appear more effective than it really is. The original article finds that in a large region around Mumbai, reservation seats in 1997 approximately doubled the number of female candidates in the following elections in 2002. Moreover, the author argues that women are 5 times more likely to win post-quota seats than other seats. In spite of the random assignment, this encouraging result may have limited interpretations. The limitation comes in part from the fact that the quotas are not withdrawn in 2002 elections. There is scientific literature suggesting that the treatment effect is smaller than that stated by the author of the original article. This natural experiment highlights the fact that comparability issues can be present even when the treatment is randomly assigned. It is not clear that one should analyse a subsample of the data in which there are no reservations in 2002 and extrapolate conclusions to a situation without reservations. The main point of this example is that in natural experiments, the selection of treatment and comparison groups is not trivial. In most natural experiments, researchers have to make additional assumptions to derive valid causal inference. Despite its clear limitations, sometimes the best way to tease out causality from coincidence justifies the use of natural experiments. The imposition of additional assumptions is particularly acceptable when a treatment is difficult or impossible to randomize. The effect of immigration on local wages is one of those treatments. I will now present a landmark natural experiment used to analyze the effect of immigration on wages using a historical event in the country of Cuba called the Mariel Boat Lift. From the early 1960s, the United States of America encouraged Cuban citizens to emigrate using a variety of policies. Cuba is an island 90 nautical miles southeast of US territory. There were serious political tensions between its communist government at the time and the Americans. In 1980, the Cuban president, Fidel Castro, opened the doors of the port of Mariel, leading to the massive emigration of more than 120,000 Cubans to the US in 6 months, from April 22nd to October 30th, 1980. The event is widely known as the Mariel Boat Lift. The Cuban refugees from the episode are known as Marielitos. Based on the settlement pattern of earlier Cubans, it is widely assumed that about half of the Marielitos settled permanently in Miami. Unlike previous Cuban immigrants, the Marielitos were mostly low-skilled individuals. Around 60% lacked high school degrees and just 10% were college graduates.
Al esfuerzo y al heroísmo de una revolución, no los queremos, no los necesitamos.
The Mariel Boat Lift created an exogenous increase in the unskilled population in Miami and an opportunity to study the effects of this type of immigration on the native labour market. In theory, a supply shock of the magnitude of the Mariel Boat Lift could depress the wages of local workers, particularly the poorly educated. The conclusions from this natural experiment are mixed. In 1990, the economist David Card looked at the bottom quartile of workers in Miami and concluded that the Mariel Boat Lift had had virtually no effect on the wages of low-skilled non-Cubans. He also found no evidence of increased unemployment. His article was highly influential. 26 years later, in 2016, the Mariel Boat Lift was in the policy spotlight again. The economist George Borjas revisited the boat lift and contradicted Card's conclusion by using a different definition of low-skilled labour force. The contradictive results from Card and Borjas show that the conclusions drawn from natural experiments depend on the studied treatment and comparison groups. Unfortunately, because of the fundamental problem of causal inference, we will never know the true counterfactual. We don't know what would have happened to the Miami income distribution had the Marielitos not arrived. This mass immigration event produced an exogenous increase of the labour force, but was also the source of profound social changes in the metropolitan area of Miami. Among the Marielitos were several hundred inmates from Cuban mental hospitals and jails. Many of them were arrested in the United States and experienced long incarceration periods due to a legal limbo that would not allow them to be deported to Cuba nor to re-enter the American society. The Mariel Boat Lift had major consequences on the general perception of immigrants, on federal immigration policies, and even on presidential elections. All these treatment effects are confounded in the data. Conclusions. Natural experiments are observational studies of sharp, well-defined but unplanned changes. They hinge on identifying an uncontrolled but opportune treatment, typically of a kind or on a scale that could not ethically or feasibly be implemented using random selection methods. More than an evaluation method, natural experiments are an identification source. Opportunities that must be recognized and wisely exploited using econometric tools. Natural experiments are more susceptible to bias and confounding. Their analysis requires a good understanding of the process determining exposure to the treatment and careful choice of the studied treatment and comparison groups. Special care is needed in the reporting and interpretation of evidence from natural experiment studies. Testing of additional assumptions is vital, and causal inferences must be drawn with care.